is that, every character, so suppose this is D character, every ASCII character will be encoded in 8 bits, or a character will be encoded according to ASCII code in 8 bits. So how many pages we are downloading per second? 100 pages. For each page, 100, there are 100 pages. For each page we have 24 lines, and each line on an average contains 80 characters, and each character is represented by 8 bits. So these many bits we need to transfer in 1 second, because 100 pages per second we need to download the document. So if these many bits are required, the speed required will be the multiplication of all, and this is 1.536 Mbps. So this is how you compute the bit rate for any non-periodic digital signal, and you count the number of bits required, and therefore you can find the bit rate. Similarly, for voice channels, as we discussed yesterday, for digitized voice channels, we need 4 kilohertz of bandwidth for analog voice signals, which like I'm transmitting my voice. So I'll be needing, for any audio messages, for any voice channels, we'll be needing 4 kilohertz of bandwidth. So 4 kilohertz of bandwidth, and we require twice the highest frequency. 2 samples per hertz are required, and each sample contains 8 bits. So 2 into 4000 multiplied by 8, that is 64 kbps of bit rate is required. So another one is, if you have a high definition TV, how much bit rate you will require for high definition TV. So we assume that high definition TV screen is normally of 16:9 ratio, and it has a resolution of 1920 by 1080 pixels per screen. So, and if screen is renewed 30 times per second, the screen is renewed 30 times, and 24 bits are represented to for colored television. For every pixel, we'll be using the RGB scheme, red, green, blue color. For every color in the pixel, we'll be using 8 bits. For red, we'll be using 8 bits. For green, we'll be using 8 bits. For blue also, we'll be using 8 bits. So in all, for each pixel, we'll be using 24 bits for color representation. 30 times per second of screen is renewed, and this is the resolution of the TV. So the speed is approximately 1.5 Gbps is required. This much bit rate is required as per our theoretical calculation. But after compression, we can reduce this speed to 20 to 40 Mbps. After compression. So this is how you compute the bit rate. So for any non-periodic signal and for digital non-periodic signals, we compute bit rate. So because we cannot we cannot compute the bandwidth based on frequency and the time length or the period, because they are non-periodic. So next one is bit length. How do you compute the bit length? We discussed the concept of wavelength for analog signals. For analog signals, if it is a sine wave, we say the wavelength. The one cycle, so the time required to complete one cycle is known as the wavelength. That is the length of the period. But the distance, but in case of non-periodic digital signals, we consider bit length. So it is the distance one bit occupies on the transmission medium. So if we are saying we have a digital data to be transmitted, suppose this one. So one bit is transmitted in this time duration. So this is the time for bit transmission. This is bit length. So on the timeline, the time required for transmitting single bit or 2 bits is the bit length, or a single bit is the bit length. So propagation speed, and it depends on two things, on the transmission media. So depending on the transmission media, the propagation speed will vary, and the bit duration, if you multiply both the things, you will get the bit length. So these are the two aspects of digital non-periodic signals. Then we left yesterday on the transmission impairments. So we were discussing that there are various causes of signal impairment, and the data or the signal which we are supposed to receive. We are supposed to receive the signal as it is, what the sender has sent. So we assume that there is no noise on the channel, there is no transmission impairment, and it should be received as it was sent from the sender side. But we have three types of causes of impairment: attenuation, distortion, and noise. And attenuation, we discussed yesterday, that because of the electrical signals which are transmitting through the wire, they generate heat. And just hold on for a moment. Hello. So we were discussing about the attenuation. Attenuation is basically the heat, because the signal dissipates over a period of time after the generation of the heat. Therefore, it attenuates the power of the signal. And this we discussed it yesterday, decibels and attenuation or the signal strength, for making the signal strength same after a period of time, because we are transmitting it over this long distance from point 1 to point 2. We have to find out how much signal has lost its strength, and after amplification of the same signal, we have how much strength we have gained. So that we have to compute, and for that we discussed yesterday that we have to use decibels. Okay, so we discussed that decibels is normally computed in the form of power. So power gained after the amplification is P2, power gained, power before the signal strength in the terms of power before amplification. So these two powers are P2 and P1. Okay, and we compute using the decibels formula, 10 log 10 P2 upon P1. And we discussed also that power is represented as square of voltage. So the decibels formula will become 20 log 10 V2 upon V1. Now, few examples for computing the decibel or power attenuation or power amplification. We can compute how we should compute. So suppose a signal travels through a transmission medium and its power is reduced to 1/2. So this means that P2 is 1/2 of P1. In this case, the attenuation is loss of power can be calculated as 10 log 10 of P2 upon P1, and P2 is half of P1. So 0.5 P1 upon P1, and that becomes 10 log 10 of 0.5, and that is minus 3 decibels. So a loss of 3 decibels is equivalent to losing 1/2 the power. So we can say if we have lost 1/2 of the power after attenuation, we have lost 3 decibels. Then another computation can be seen in another example. If after amplification the signal power has been increased by 10 times, then we can say P2 is 10 times of P1. So 10 log 10 P2 upon P1. So 10 log 10 times of P1 upon P1. So that is 10 decibels, because log 10 of 10 is 1, so 10 decibels. So it has gained 10 decibel strength. So I hope you can go through these examples, or should I discuss these examples 3.28, 3.29? Students? Good morning, students. Are you there?
Yes, ma'am.
Yes, ma'am.
So these are just computations of log. So you can just go through examples 3.28, 3.29, and 3.30. And if you want me to discuss now, I can discuss it right now. What do you say? Should I discuss it now? It'll take 2 minutes, 3 minutes.
Yes, ma'am, sure, ma'am.
Okay, I'll discuss. So one reason that engineers use decibels is that decibel numbers can be added or subtracted, because log numbers can be added and subtracted. So and they can be cascaded. So instead of basically doing other modifications and computing it, you can just do additions and subtractions directly in logs, and that is much easier. So you can see that this example 3.28. So if we say between 0.1 and 2, the transmission medium has a loss of 3 decibels, minus 3 decibels. And after 0.2, an amplifier is put between 0.2 and 0.3, and the signal has gained the strength of 7 decibels. So it has been amplified. Again, from 0.3 to 0.4, there is a loss of minus 3 decibels or loss of 3 decibels. Minus means it is a loss. So it has been attenuated by 3 decibels. So how can you can directly add and subtract the decibels. So you say minus 3 plus 7 minus 3 equals plus 1. So there is a total gain of 1 decibels in the signal strength from 0.1 to 0.4. This is quite easy. Then example 3.29. Sometimes the decibel is used to measure signal power in milliwatts. So normally the measurement unit for power is watts. For voltage, it is volts. So milliwatts also you can use for measuring the signal strength. Usually we use in watts, but sometimes we can use milliwatts also if it is a small device. So in this case, it is referred to as dB of M, and it is calculated as dB of M is 10 log 10 PM. So instead of only P, we'll have power in milliwatts, PM. So if you would like to compute it like this, so you have to calculate the power of a signal in milliwatts if dB of decibels of milliwatts is equal to minus of 30. So how will you compute? dB of M is 10 log of 10, where we know that this is 30, minus 30. So minus 30 is equal to 10 log 10. So 10 log, so minus 30 is basically log 10 of PM, because it was 10 log 10 of PM. 10 log 10 of PM is equal to minus 30. So this 10 will divide minus 30, that will become minus 3. So minus 3 is equal to log 10 of PM. Therefore, PM is, so if you reduce this to normal and you remove log, it will be 10 raised to power. So log of 10 will be a power here. So 10 raised to power minus 3 in milliwatts. Is that clear to all of you? Do you know log?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So example 3.30, the loss in a cable is usually defined in decibels per kilometer. So when you say cable is the signal loss in a cable, so we say per kilometer. So if a signal is traveling, suppose at the rate of 3 kilometers per hour or something like that. So normally when the signal is electrical signal is passing through a coaxial cable or twisted pair, so we say that and we compute normally in the form of decibels per kilometer. That ways we compute the signal strength. So if the signal at the beginning of a cable is 0.3 decibels per kilometer or minus 0.3 decibels per kilometer, it has a power of 2 milliwatts. What is the power of the signal at 5 kilometer? So we say the attenuation is, so the loss in the cable in decibels is 5 into minus of 0.3, because per kilometer the decibels, the loss is defined as 0.3, minus 0.3. So this is the loss per kilometer. For 5 kilometers, we have to first calculate the loss. So the loss is 5 into minus 0.3, that is minus 1.5 decibels. So now compute the power after 5 kilometers. So 10 log of 10 P2 upon P1, and we say this loss between, because we are not saying there is a gain in power, because we are having minus sign, minus of decibels. So decibels is already given after 5 kilometers. So for 5 kilometers, we have said minus 1.5, which is equivalent to 10 log 10 of P2 upon P1. So P2 upon P1 is 10 raised to power minus 0.15. That is, if you see the log table, power, and if you see this one, this will be 0.71. So then P2 is equal to 0.7 of P1, and we say it has a power initially when it started beginning of the cable, the signal has a power of 2 millivolts. So P1 we know 2 millivolts, and it is 0.7, approximately 0.71. We have approximated to one digit 0.7, and it becomes 1.4 millivolts. So because it has been attenuated from the beginning of the cable, and at 5 kilometers it will come down to 1.4 millivolts. So instead of 2 millivolts, it will come down to 1.4 millivolts because of the minus 0.3 decibels per kilometer. So after 5 kilometers, it will be reduced to 1.4 millivolts. I hope the calculations are clear and the concept is clear to all of you. So these are the different ways in which you can compute the loss in the signal strength or gain in power of the signal strength. Now the next to signal impairment, transmission impairment, is distortion. Now what happens, you must have studied in physics, or maybe you must have heard somewhere that any analog signal normally contains different frequencies. So it is a combination of frequencies. All the analog signals are combination of frequencies. So it has various components. So when you have a higher frequency component, it may be distorted more due to some of the distortion elements. But some lower frequency components may be distorted less, or the other way around. There may be some elements in the transmission medium which distort the low frequency signal, but they distort less the high frequency signals. So what happens when the distortion occurs, the signal, basically they inhibit some of the signals and some of the frequencies, but they allow some of the frequencies to pass through normally. So what happens when I'll give you an analogy from the real life. Now suppose you are a team, a composite signal. A composite signal is basically having multiple frequency components. So suppose a signal contains 3 frequency components, F1, F2 and F3, and in real life, suppose you are 3 friends, F1, F2 and F3. You can only start at the same time, and you can only start the project after coming to the college on the same. If you reach in the college on the same time, then only you can start the project. Otherwise your project will be delayed, and it will not be running smoothly, and you may miss some of your deadlines. So what will happen, F1 is starting from her home, F2 is also starting from her home, F3 is also starting from her home, but F1 will find more traffic on the route, F2 will have less traffic, and F3 will not find any traffic. So what will happen, F3 will reach first, F2 will reach a little later, and F1 will reach after 1 hour. So what will happen, you will miss your deadlines. That is the problem. So your all the schedule of the project will be distorted, and you will not be able to accomplish the project tasks for that day efficiently on time. So that is because of the distortion, because you have been inhibited by the traffic differently. One of the friends has been inhibited, she was stuck in the traffic more. One of the friends was stuck in the traffic for a little bit of time, and another friend, she could come without any traffic congestion. So same is with signals. When we have a composite signal, there is a difference in the delay, and that has been created by different signals, frequency components, and they may reach out of phase. Now suppose this is an example. Now this is a composite signal which is sent actually, but this signal, you can see there are 2 signals. One is the actual sine wave, this one, and another one is this one, smaller one, and third one is this smaller sine wave. So it is basically a composite signal of 3 constituent signals. This is at the center side. But what will happen at the receiver side, because they have been distorted differently by the same transmission media. Now they are having the same transmission media, they are passing through the same cable, but because of their individual frequencies, they will be distorted differently and they may reach out of phase. Out of phase means, now see here, this sine wave is starting and it is in phase, but this was starting its cycle at this point, but here when it was received by the receiver, it's this point is received by the signal when this point of the first composite signal was received. And you can see there was a positive cycle when the sender sent this third component, the smaller component, but at the receiver side it received the negative component of the third smallest sine wave. So if you'll add up these three sine waves, the composite signal received will be the distorted one, so it will not be in its original shape. Is that clear to all of you? Distortion?
Yes, ma'am.
Yes, ma'am.
Then noise. So this is the third component of impairment, third type of impairment that can occur in any electrical signals or analog signals in the transmission during the transmission of the signal through the transmission media. So noise is another cause of impairment. Now there can be thermal noise, induced noise, crosstalk and impulse noise, and it may corrupt the signal. Sometimes like not nowadays, but in when the normal telephone systems, you used to have noise. Is there any request? Okay. So noise can be of any type. So suppose a signal is being transmitted through the wire. This is the transmitted signal, but due to some electrical spike, there is a sudden surge or spike in the electrical signal. एकदम से power shoot करता है, spike करता है, and your signal changes to something else. So the received signal will be distorted. So here it should be like the amplitude should be this much, but because of noise it has been interpreted as high amplitude. So the signal which was carrying some data, analog data or maybe some digital data, it is misinterpreted as something else because the signal itself has been impaired and it has created some noise in between, so it may be interpreted differently. So the data you want to transfer through this signal may be something else, you may interpret it as something else. So what we were saying, like when in earlier days you used to have this landline systems. आपने कभी सुना है मम्मा को या आपने कभी बचपन में एक्सपीरियंस किया कभी लैंडलाइन पे when you were talking to someone and suddenly somebody else will be in your conversation. So behind suppose you are talking to your friend and in between you are able to hear somebody else's conversation also. Have you experienced that?
No, ma'am.
No? So it used to happen in earlier days when we were using the normal telephone system that uses twisted pairs or coaxial cables. So in those days we were used to hear some days at some points of time. So basically the sending antenna and the transmission.
Yes, ma'am. Cross connection.
Yeah, cross connection, crosstalk was also there. So when one signal was going through one wire and there was some parallel wire, there was some signal which was interfering with the first signal. So the signals were interfering. So that was crosstalk. Then there must be, there can be some induced noises also because of the motors and appliances running near your transmitter and receiver. So like normally when I am, you must have, this is one of the examples, induced noise. Like I am using my this mobile phone also, and I am using my system also, and I got a call. So or I am just opening the speaker at both the things, and I am logging in into Zoom. You have seen that, you have experienced that. If you have logged in from two places, one from your laptop, one from your mobile phone, and there is an echo. And if you are the presenter, there is an echo. So normally it happens. So that is induced noise. So it is because of the other device, which is another mobile phone or laptop, due to which echo is there. Or This is the latest example, or otherwise, suppose there is some other motor running near your laptop or mobile phone when you are talking or when you are transmitting the signal. It is also generating some EM waves, because you must have studied in physics, when a electrical signal is transmitted through a wire, there is an electromagnetic field generated in a circular area around the wire. Have you
Yes, ma'am.
studied that? So that is
Yes,
EM field आपका generate हो जाता है. उस वजह से if there is some appliance running near your transmission device, sender device, sorry, that can induce a noise in the current signal transmission. So these are the types of transmission impairments. Now, in case of noise, like in this attenuation, we discussed how to compute attenuation, where there is a loss in the power of the signal or there is a gain in the signal strength. We used measurement of decibels to compute the loss and signal gain in the signal strength. But for noise, we have another parameter known as signal to noise ratio. So to find the theoretical bit rate, we need to define the signal to noise ratio. This is average signal power divided by average noise power. So now suppose this is a signal. So for high SNR, we say the signal is distorted less. So if the average signal power is more and average noise power is less, there will be high SNR. That means noise is less, therefore your signal will be distorted less. So this was a signal and this was high SNR, means there was less noise power. So high SNR means signal plus noise, and you'll have a less distorted signal. So at least you can say this is this type of a signal, digital signal, and the highest amplitude is near in between here and lowest is near this point. So it is comparatively less distorted. But if you have a less SNR, that means average noise power is more and average signal power is comparatively less. So it will have a low SNR. In case of low SNR, the signal will be distorted more. So you can see this was the original signal. The noise power is more, therefore low SNR, and because of that, signal plus noise, the actual signal we have received at the receiver has more distortions, and we could not find out what was the actual signal. Is that clear? So actually the ratio is the wanted signal to what is not wanted, that is noise. So high SNR means the signal is less corrupted by noise. Low SNR means the signal is more corrupted by noise. So SNR is a ratio of two powers, as we have seen, average signal power and average noise power. So for computing SNR decibels, 10 log 10 of SNR. That's simple, the same formula. So now we have some examples. The power of a signal is 10 milliwatts and the power of the noise is 1 microwatt. What are the values of SNR and SNR dB? So we are given, this is in microwatts, this is in milliwatts. So one of the units have to be converted to the other. So instead of converting microwatt, this is a smaller one, you have to convert milliwatts into microwatts. So this is 10,000 microwatts. 10 milliwatts will become 10,000 microwatts upon 1 microwatt. This is SNR. So this is noise power, this is signal power. So signal power upon noise power is SNR, that is 10,000. So SNR is 10,000. Now for computing SNR dB, we need 10 log 10 of 10,000, which is 10 log 10 of 10,000, 10 raised to power 4. So 4 comes here. 10 log 10 of 10 is 1. So this becomes 40. So SNR is 10,000 and SNR dB is 40. So the values of SNR and SNR dB for a noiseless channel are, because we say noiseless channel, therefore we say there is no power in the noise. There is no average noise power. So that is 0. So we say SNR for noiseless channel is signal power upon 0, which is infinity. Because so, and similarly 10 SNR of dB is equal to 10 log 10 of infinity, which is also infinity. So but this is an idealistic case. We never have SNR of infinity or SNR dB of infinity, because there is no actually in real life, there is no transmission media which does not generate any noise impairment. So that is theoretical thing. Is that fine?
Yes,
Can
ma'am.
you explain this example again? 3.32, ma'am.
Yeah, because we say this is for noiseless channel. Noiseless means there is no noise. Okay.
Yes, ma'am.
No noise means SNR formula says average signal power upon average noise power. So average signal power, whatever it is, signal power is suppose P and noise power is 0. Noiseless means there is no noise. That means there is no noise power 0. No signal with any power 0. So that will be signal power any P, any value.
Yes, ma'am. Yes, ma'am.
So any value upon 0 is infinity. So that will be infinity. So in real life, there is this is an idealistic case. We cannot achieve
Yes, ma'am.
infinity for SNR and SNR-DB. Fine.
Yes, ma'am.
So next, I think, so we have discussed 3.3, 3.4. Now we have to go this 3.5. Now, data rate limits. A very important consideration in data communication is how fast we can send data in bits per second over a channel. Now, it depends on the three factors: the bandwidth available to us for sending the data, the level of the signals we use, the quality of the channel, that is the level of noise we use. So basically, for calculating the data rate, we have two theoretical formulas. One given by Nyquist for noiseless channel, we assume there is no noise, and another by Shannon for noisy channel. So we'll be discussing in this section about noiseless bitrate and noisy bitrate, or noiseless channel bitrate and noisy channel bitrate. So Nyquist says that we don't have any noise on the channel. So based on the noiseless channel assumption, we say the bitrate of any transmission media or any transmission channel can theoretically be up to a maximum of 2 into bandwidth multiplied by log 2 of L. Now we discussed bandwidth yesterday. Bandwidth is the range of frequencies, the spectrum of the composite signal, and the highest frequency minus the lowest frequency is the bandwidth. So twice the bandwidth multiplied by log 2 of L. Now what is L? L is the number of signal levels used to represent the data, and bitrate is the bitrate in bits per second. Now what do you mean by the signal level? That we'll discuss now. So suppose we are saying we are using 2-bit levels, 0 and 1. So lower frequency, suppose we say plus 5 volts, 0 volts is 0 and 10 volts is 1. So these are two logical signal levels. So my signal, my electrical signal or my analog signal, or maybe my digital signal, whatever it is, my signal is only having 2 levels of representation, and it is only representing 1 bit per signal. Okay, so 1 bit per level. So if we increase the number of levels, log 2 of 2, suppose I am using 2 signal levels to represent my zeros and ones. So log 2 of 2 is 1. So directly bitrate will be twice into bandwidth. But if we increase the number of signal levels, so we are saying we can increase the bitrate. But theoretically, if I say I am using 8 levels for signaling. So if I say 0 volts for representing, now suppose I have 8 levels. How many bits I can represent with a single number? You have done binary number system?
Can you repeat?
Yes, ma'am. Yes, ma'am.
So 8 can be represented in how many bits?
4 bits.
4 bits, and
Bits,
7
ma'am.
can be represented in 3 bits. So from 0 to 7, if we use only 3 bits, so from 0 to 7, I can, in 3 bits, I can represent 8 different numbers, 0 to
Yes,
7.
ma'am.
Fine. So that means if I use 8 different voltage levels, 8 different signal levels, so I can represent, I can send 3 bits in that. Got my point?
Yes, ma'am.
So if I say in one time, if I'm saying I am sending 0 volts, it will be represented as 0, 0, 0. So in one time, I am sending 3 bits. If I say 1 volt is representing 1, digital 1, so that is 0, 0, 1. So I am sending 3 bits. If I need to send 0, 1, 0, that is 2. 2 volts I can send. So 2 volts will represent another signal level. So and then 3 voltage, 4 volts, 5 volts, 6 volts, and 7 volts. So having 7 different voltage levels for any electrical signal can send 3 bits per signal level. So if I'm sending only 0 volts, that means I'm not sending any electrical signal and the signal is absent 0 volts, then it is represented as 3 0 0 0 0. If I say I'm sending 5 volts, it will be represented as 1 0 1. It will be also representing 3 bits. So what I'm doing is I am increasing the bit rate. Is it fine? So by increasing the number of levels log 2 of L, so if I am increasing L, the number of L's, I can increase the number of bits transferred. So now if I say I am using 16 signal levels, 16 different signal levels, 0 to 15. So maximum 4 bits per signal I can send. I hope I am clear. My point is clear.
Yes, ma'am.
It is clear to you. So similarly, if I use 64 signals, 64 signal levels, 0 to 63 voltage, I can represent how many bits? If I have 64 signal levels, how many bits I can represent in 64? Students?
Yes, ma'am.
Ma'am, 0 to 63 we can represent in 7 bits, and in 60 if we include 64, then it will be 8.
I'm asking about 63.
Yes, and then 7 bits.
So if I use 64 signal levels, I can represent 7 bits per signal level. But this is theoretical thing, okay? So I assume if I become very greedy and I say I can increase my signal levels up to 128 or 256, I can increase the bit rate, and on the same bandwidth I will have more data rate. No, more bit rate you cannot achieve. This is just the theoretical part. But see the hardware part, see the physical implication or the practical part. There is a limit, because if I am sending 0 to 63 volts and I am having 64 bit signal levels, I'll need to have a hardware, the sender and the receiver, which can have those voltage levels. So my sender should be able to encode my signal or send my signal in those voltage levels separately, and my receiver should also be tuned to the energy levels or same voltage levels. Fine. So normally you must have seen your, suppose I'll give you a real life analogy. If you have a radio device, suppose. So if you're tuning into different radio channels, different FM channels, you need to tune it to a receiver. That is your frequency channels in the mobile phone or your radio receiver. And you have to set the channels. Like what is Radio Mirchi? 98.4.
Yes, ma'am.
Okay, so 98.4, you have to tune in and you have to set that frequency. So if you want to connect to Radio Mirchi, it will be 98.4, or maybe something else, 91 megahertz also, or 90 megahertz. There are so many channels, fine. So you need to tune your receiver to different frequency levels. This is only for the receiver part, because the sender is already the FM channels, they have set their frequencies. Now suppose I am assuming that I am doing a communication, so my hardware receiver and hardware sender should be able to distinguish between the different frequency levels physically. So if I'm sending 0 volts, it should be interpreted as 0 volts. I'm sending 1 volts, it should be interpreted as 1 volts. So my hardware sender device and the hardware receiver device should be able to distinguish between the different signal levels, and it has to be designed appropriately. and it has to be more sophisticated also for receiving so many different signal levels. So that is really near to impossible, or that will be that won't be cost effective. If we increase the bit rate, my hardware will also be more expensive. For having such a sophisticated physical device, I'll be investing more. Is that clear to all of you?
Yes, ma'am.
And if my receiver and sender are not sophisticated, and it is not able to distinguish correctly between the 64 different levels, then in that case my signal reliability is reduced, because it will not interpret it correctly. So 2 volts sometimes may be interpreted as 3 volts, and then the entire data interpretation will be wrong. The message interpretation will be wrong. So increasing the levels of a signal may reduce the reliability of the system. So this is the theoretical limit, and we have not included any noise component in this. This is Nyquist bitrate. Now the examples are, does the Nyquist theorem bitrate agree with the intuitive bitrate described in baseband transmission? So they match when we have only 2 levels. So we said baseband transmission, the bitrate is 2 times the bandwidth if we use only the first harmonic in the worst case. So however, the Nyquist formula is more general than we derived intuitively. So it can be applied to baseband transmission and modulation. We'll discuss it later, okay? When we'll discuss about the transmission medium. Now this is another calculation actually. Consider a noiseless channel with a bandwidth of 3000 Hertz transmitting a signal with 2 signal levels. So the bit rate can be computed as, now the frequency bandwidth is 3000 Hertz and the signal levels are 2. So the bit rate is twice into 3000 into log 2 of 2, which is 1. Log 2 of 2 is 1, and this becomes 6000 into 1, 6000 bits per second. Now consider the same noiseless channel transmitting a signal with 4 signal levels. So same channel with 3000 Hertz of bandwidth, but now we are using 4 signal levels. So log 2 of 4 is 2, and this was 6000 into 2 is 12,000 bits per second. So we can see that increasing the number of signal levels has increased the bit rate, but that's not always possible to increase beyond a particular practical limit. Another example is, we need to send 265 kbps over a noiseless channel with a bandwidth of 20 kilohertz. How many signal levels do we need? Now we have to do the reverse calculation. We need to compute the L, the number of levels, how many we need to have. So already bit rate is given to us. This is 26 kbps. So normally this is in bits per second. So it is in kilobits per second. So we need to convert it to 1000. 265, 2,65,000, that is 265 kbps. Then we say we have 20 kilohertz of bandwidth. So bandwidth is again in, not in hertz, this is in kilohertz. So 2 into 20,000, because 20 kilohertz, log 2 of L. So using this formula, if we say log 2 L is, if you divide this by 40,000, 2 into 20,000, so 2,65,000 divided by 40,000 is 6 whatever, and then yeah, 6.625, and then log 2 of L is equal to 6.625. We take L as 2 raised to power 6.625, which is 98, near about 98.7 levels. So since this result is not a power of 2, we need to either increase the number of levels or reduce the bit rate. So normally whenever we are discussing in digital communication, every number should be a power of 2. Okay, so 98.7 is not a power of 2. So we take the nearest level and we say we reduce the, we can either make it a power of 2, 98.7, or we increase the number of levels or decrease the number of levels. So if we have 128 levels, the bit rate is 280 kbps. Or if we have 64 levels, the bit rate is 240 kbps. Fine? How? If it is 64 levels, because we will be having here 8. Log 2 of 64 is 8. Okay, and it will be 280 kbps, and then it will be 240 kbps if we use this. sorry, this will be log 2 of 64 will be 7, and then 7 into this 40 will be 280, so this will be 280 kb if we use 64 levels, and if we use 128 levels it will be sorry, for 128 it will be 280 levels, and for 64 it will be 240 kbps. Fine. So then we have noisy channel Shannon capacity. So as we have assumed in SNR also, signal to noise ratio, that normally the channels are noisy. So Shannon capacity says the capacity of a channel, noisy channel, is highest data rate, theoretical highest data rate can be bandwidth into log 2 of 1 plus SNR. So we have already seen what is SNR. It is the signal to noise ratio. So average power signal upon average noise power. And if we have SNR, we can compute the maximum theoretical capacity of a highest data rate for a noisy channel can be computed like bandwidth into log 2 of 1 plus SNR. So example is this. Now consider an extremely noisy channel in which the value of signal to noise ratio is almost 0. How it could be 0?
And if noise is 0?
Yeah, if not, no. If noise is 0, then it will be infinite. In other words, the noise is
signal. Ma'am, SNR ratio is, ma'am, that SNR will be 0, ma'am.
Yeah.
That is,
so if noise is so strong that the signal is
noise ratio, yes, ma'am.
Yeah. So if the noise is so strong that the signal is faint, so signal power is nearly fainted, or you cannot recognize the signal power, that is nearly 0. So 0 upon some maximum signal noise. Okay. So that will be nearly 0. 0 upon some number. That will be nearly 0. So for this channel capacity, the capacity is calculated as C B log to 1 plus SNR. So B log to 1 plus, because SNR is low, means high noise. 1 plus 0, B log 2 of 1, that will be B into 0 is 0. So capacity of the channel will be 0. So Shannon says if signal to noise ratio is nearly 0, that means the noise is so much that you cannot transmit a signal and it cannot be interpreted perfectly at the receiver side, and there is only noise and you can not hear it, or you can not interpret the signal power. Then in that case, the capacity, theoretically the capacity of the channel, whatever is the bandwidth doesn't matter, but because SNR is 0, then it becomes 0. The capacity of the channel, regardless of the bandwidth, will become 0. We cannot receive any data through this said channel, and we can only have noise on the channel. This is something like suppose you are basically having a mixer or a juicer running in your kitchen, and you are trying to talk to your friend on the phone. So or maybe you are driving on a highway, and there are so many cars and trucks going on, and so many horns, so many vehicles are honking. So you are not able to hear on the phone what is, or you are not able to hear any program on your car if your windows are open. So there is so much of noise, there is no signal power, you cannot hear or receive the signal properly. That is for noisy channel. Now we can calculate the highest bit rate for a regular telephone line. So a telephone line normally has a bandwidth of 3000 hertz, 300 to 3300 hertz assigned for data communication. The signal to noise ratio is usually 3162. For this channel, the capacity is calculated as, so SNR is given, bandwidth is also given, you can compute the capacity of the channel. So 3000 is the bandwidth, 3000 log 2 of 1 plus 3162, which is 3000 into 11.62. which is 34,860 bits per second. This means the highest bit rate for a telephone line is 34,860 kbps. If we want to send data, 34.860 kbps, sorry. I told you 34,000. So if we want to send data faster than this, we can either increase the bandwidth of the line or improve the signal to noise ratio. So there is there are two chances, that either improve the signal to noise ratio or you can increase the bandwidth. In that ways, you can increase the capacity of the telephone line. Now, signal to noise ratio is often given in decibels, as we have seen. So if SNR dB is equal to 36 and the channel bandwidth is 2 megahertz, so using the Shannon theorem or Shannon capacity capacity formula, you can first compute SNR from SNR dB. So SNR dB is equal to 10 log 10 of SNR, because we are given SNR dB. So first, because capacity formula uses SNR, not SNR dB, and we are given SNR dB, so we have to compute SNR from SNR dB. SNR dB is 10 log 10 of SNR. SNR is 10 of SNR dB upon 10. SNR now becomes 10 to the power 3.6, which is 3981. And then we can apply the form of Shannon theorem or Shannon capacity formula, which is 2 into 10 to the power 6. 2 into 10 to the power 6 is because it is 2 megahertz. So 2 into 10 to the power 6 log 2 of 3982, because 1 plus SNR and SNR is 3981. So it becomes 3982 log 2 of 3982, which Mbps. You can use your calculator, scientific calculator, to compute these values, but I hope the formula value filling is clear to all of you.
Yes, ma'am.
So when the SNR is very high, if SNR is high, what does it mean? If SNR is high, what is the implication? SNR is high means we have negligible noise. Because SNR formula says, signal to noise ratio says, average power of the signal upon average noise power. So it is very high means there only a signal power component and there is negligible noise power component. Okay, so SNR is very high, we assume SNR plus 1 is almost same as SNR. This is mathematics, so approximation, because if it is too high, like this one, 3981, so and we added just one, so it becomes 3982. So similarly, we say if SNR is so high, we can assume that SNR plus 1 is equal to SNR, is same as SNR. So in this case, theoretical channel capacity will become bandwidth into SNR of dB. So in only those cases when SNR is so high that we can take only SNR for SNR plus 1, we can replace log 2 of 1 log 2 of 1 plus SNR in the formula with SNR dB. Okay, so in the previous example, because 3981 was too high in comparison to 1, so instead of taking log 2 of 1 plus SNR, we are taking directly as 2 megahertz into SNR of dB. So 2 megahertz into 36 divided by 3. Why? Log 2 of why it is 36 by 3?
I think they have put the value of SNR dB here.
No, SNR dB is 36. But why divided by 3? Why divided by 3? Have they taken log? No. Who's that joining now? Is anyone joining now? No. Okay, I'll find it out. Fine. Why it is 3 here. I'll let you know tomorrow, okay? Now, using both the limits in this, in practice, we use both the methods, the Nyquist method and the Shannon method, to find the limits and the signal levels, find the limit on the capacity of the channel and signal levels. So now in real life, we can compute both. So we have a channel of 1 megahertz bandwidth. The SNR for this channel is 63. What are the appropriate bit rate and signal level? So using the Shannon formula to find the upper limit, just hold on. Okay, so if we have an SNR of 63 for a channel and the bandwidth is 1 megahertz, so Shannon formula for noisy channel, because it has given SNR, so it is a noisy channel. So we have the capacity formula as B log 2 1 plus SNR. So this is 10 raised to power 6 because this is 1 megahertz and the bandwidth should be hertz. So it becomes 10 raised to power 6 log 2 of 1 plus 63, which is 64. Now it becomes 64. So log 2 of 64 is 6. So 10 raised to power 6 into 6 is,
Shouldn't it be 7?
just hold on. No, it should be 6. For 7, it should be 28. Log 2 of 64 is 6. Why? Because 2 raised to power 6 is 64, na? If you take 6 in front of this, 6 into 10 raised to power 6, so log 2 of 2 is 1. 2 to the 4 to the 8 to the 16 to the 34 to the 64. So 2 raised to power 6 is 64. Got it? 2 raised to power 6 is 64. So that will be 2. So here log 2 of 64 will be log 2 of 2 raised to power 6. So power component will come here, 6 into 10 to the power 6, that will become 6 Mbps, and log 2 of 2 will become 1. Clear?
Yes, ma'am.
So the Shannon formula gives us 6 Mbps. So this formula for noisy channel SNR, if SNR is given, we have computed 6 Mbps using this formula. So this is the upper limit. For best performance, we choose something lower, that is 4 Mbps. So we use a Nyquist formula, find the number of signal levels also. So for Mbps, if we use 4 Mbps, then find the signal number of levels. So 2 into 1 megahertz, because the capacity of the channel was bandwidth of the channel was 1 megahertz. So this is the required bit rate, we say using Nyquist theorem or Nyquist formula, 2 into 1 megahertz into log 2 of L. So if we are given all these quantities, we can always compute L as 4. Fine? Is the computation clear to all of you?
Yes, ma'am. Yes, ma'am.
Okay. So I think we are done with this in the guidelines 3.4 to 3.5. So we'll start with this one and this one. So we have one more class now. You want to have a 5 minutes break?
Yes, ma'am.
Okay.
No, ma'am. 15 minutes break, ma'am.
Huh? Why is Saloni joining now? Yes. Students, you want a break now, or I should start another topic right now?
Ma'am, 15 minute break.
15 minutes break. It is a continuous class, but you can come back by, it is 11:10 now, you can come back by 11:15, okay? Then I'll take the attendance of the 2 classes.
Okay, ma'am.